Welcome to the CS415 video about virtual memory. So with virtual memory, we're trying to solve three key problems: protection, relocation, and sharing. So a typical process has a process control block, some code or instructions to execute, a heap, and a stack. Now within the code, we have pointers like branches and loops that point to different sections of a code. And we also have pointers that point into the heap and even possibly into the stack. So if we take this process image and we store it at a certain spot in our physical memory, and that's what this box is here, is our physical memory, then everything works great. But let's say that we need to take it out of memory for a while and store it on the disk, and then put it back into a different spot. Now, all of these pointers need to be updated. So we need a way to relocate memory. Now, the reason why we might do that is because this process is busy waiting for some I/O, and we want to open up and free available memory for a process that actually wants to run. That's why we would take a process out of memory, and then later on, when we go to put it back, maybe this memory is taken, but we have some available memory in a different spot. So we might want to relocate it. Now, another thing is we don't want one process to be able to reach in and look at memory of another process. That would actually be a hacker's dream. They can get a little program in there, and then it can spy on some memory and view passwords, encryption keys, and a lot of other stuff that we that are obviously sensitive. So we need to protect processes. Now, there's just hackers, but if one process messes up the memory in another process, that could cause this process to not work right. And finally, there are some things like shared libraries and even some shared data that processes can share, and we don't want to make two copies of those in memory for each process. We need a way to share certain parts of the memory between processes. Now, virtual memory is a way that achieves all three of those goals and comes with another bonus, and that is that memory that the process thinks it has can be bigger than the actual physical memory that the machine has that it's running on. Now, some of the memory might be located on disk, and other memory might be located in the physical memory. So this is the actual physical memory of the computer over here on the right, and this is what the process thinks memory looks like. So what we do is we divide memory into equal sized chunks called pages. And then our physical memory is also divided into equal sized chunks called page frames. And that means we could take one page and slide it into our physical memory inside of a page frame. Now, for simplicity, let's assume that we're working with a 16-bit machine, and that means each memory address is 16 bits wide. Now, we're going to take the memory address and we're going to divide it into two parts. The upper bits will become the page index, and the lower bits become the page offset. And the way that works is whatever number is stored in the top 4 bits tells us which page this is located in. So which one of these? Now the offset down here tells us where inside of the page the data that we want is located. So this tells us where inside of the page it's located, and the index tells us which page it's on. So since there's 4 bits for the index, that means we can have a total of 16 pages. So each process that's running on our computer can have a total of 16 pages. Now that doesn't mean it's going to use it all. It's only going to use the pages that it actually uses. So if it doesn't use a page, we won't create a page for it. Now each page, since there's 12 bits to index into it, that means that we're going to have 4 kilobytes worth of data for that page. I went ahead and numbered each page of our process and also each page frame of our physical memory. So what we can do is we can decide to store this page in any one of the page frames here. So I'm just going to write 2 right here to pretend that this page is stored there in physical memory. So now what we need to do is translate. Whenever a process asks for memory, either to read the next instruction out of memory or to read some data, that we're going to translate the address that it thinks it's reading from, a virtual address, to the physical address of where it's really located. And how we're going to do that is we're going to take the address, the process says, I want memory from this address. We're going to take the index bits, and that'll tell us which page of the virtual memory it is on. And we're going to replace them with the physical location of where that page is. That way, the process thinks it's addressing some memory right here, but we really stored it down here. And when it requests that, we translate it so it gets the memory from the right spot. So how are we going to translate those addresses? That's where the page table comes in. And so the page table has a page table entry. So each row is a page table entry for every page that the virtual or that the process could possibly address. So this virtual address space has, each area has a page table entry. Now, at the very beginning of our program, we have this very first bit, which we're going to probably mark as 0, saying that these page table entries are not valid. That means we've never used them before. Now, the next bit will be used to say whether or not this page is in memory or on the disk. So if it's not valid, it's obviously not in memory, but if it is valid, then some pages might not be in memory and other pages might be in memory. So that's what this bit is used for. And then finally, if it is in memory or if it's on the disk, we need to know where it is. So remember before I said that page 2, we decided to put it into physical memory at this page frame number 6. We stored the number 6 saying that page 2 is located at page frame number 6. Finally, we also have a bit to say whether or not this page has been used, and usually every time the operating system needs to update the page table, it'll update the table and set all these bits to 0, and then as they get used, it'll turn the flag, it'll flip the bit saying that it has been used. That way, the operating system can make better decisions on what pages should stay in memory and what pages should not. But I'm mostly going to ignore this for the rest of this video. So how does it do the translation? So the process is running. It wants some memory from this page. So it takes whatever address it gives us, it chops it in half to split it between the offset and the index. It takes the index bits, and because it's in this page, the index bits are going to contain the number 2. So it's going to go to row 2 inside of the page table entry, check to make sure it's valid. So hopefully we'll say that this is valid, and then check to see if it is in memory. And if it is in memory, then it'll replace the 2 that was the index bits with 6, and then that becomes the physical address so that it can find the actual data in our physical memory. So to get a better idea of how all this works, let's just run through a simulation with 2 processes, process A and process B. Now each process gets its own page table. That way, its addresses can translate differently than another process. And so let's start off, and process A is running. So the first thing before process A can run is, first of all, we need to know who does the translating of the memory address. And that's the physical CPU. It has, CPUs have built into them this translating functionality so that it can translate virtual memory addresses into physical memory addresses. So the CPU is in charge of translating the address. However, the operating system is still in charge of setting up these page tables. So the operating system needs to know exactly what the CPU expects for these page tables. That way it can set it up correctly. Now, one part of the CPU that does this translation is a pointer or a register that contains the memory address of where these page tables are located. So these page tables are also located in memory. I mean, that's the only place to store them. I guess you could store them on the disk, but that would be really slow to access them. And if you did your configuration right, hopefully your page table can be the exact size of one page frame. So one of these locations in memory might store a real page table inside of it instead of any of the data in the code that the process is using. So to represent that register inside of our CPU that contains the memory address of the page table, I've drawn this little box. Now, when we switch processes, one thing we'll have to do is update this memory address. So if process A is running, hopefully the memory address will be the address of processes A's page table. And when we switch to process B, then we'll update this to point to process B's page table. So process A doesn't have anything in memory. Now we might preload some code and some other stuff, but we'll just assume that it doesn't have anything in memory. So we'll start off by initializing all of the page table entries to 0, saying that none of the page table entries are valid. So process A is going to ask for memory. Most likely, as it starts to run the program, it's going to ask for memory location 00. That's usually the first instruction of our program. So it's going to ask for this, and the CPU is going to try to translate the address. Now, as the CPU translates the address, it takes the address, finds the index, and the index will be 0. It goes and finds using this pointer, it finds the page table and sees that that's invalid. So what the CPU does now is throw a page exception or a page fault. And so whenever the CPU cannot translate the address, it just throws up its hands and says, operating system, I cannot translate this address. You better take care of it. So now the operating system gets to run some code to fix this page fault. So the first thing it might do is try to select a free page frame to be able to store this memory. So we'll go ahead and select this page frame here. And so I'm just going to mark this saying this page frame we're going to assign to process A page number 0. And so the operating system needs to keep track of what page frames it's handed out and to whom. So after it does that, it's going to update the page table entry and say you're now valid, you're in memory, and you're located at physical page frame number 0. Now it's just a coincidence that it did 0, 0. It could have chosen any free page frame. So once the operating system gets all that fixed, it says, okay, I fixed the problem. CPU, try to run this, try to go again. And so now the CPU is going to translate the address. And as the CPU looks at the page table entry, now it's going to see, oh, good, you're valid and you're in memory. Okay, I'm going to replace the 0 index with 0, and that'll allow it to translate. Now the process is probably going to ask for some other memory location next. And let's say that it asks for something on page 4. So as it goes to translate the address and it looks there and sees, oh, that's invalid, the CPU will throw another page fault. The operating system will wake up. It'll say, okay, I'm going to mark that valid. I'm going to mark it in memory. And let's put that at memory location 8. So, and then it will let the CPU go to try to translate the address again. And now that the page table entry is valid, the CPU could go ahead and translate the address to physical memory as well. Now, the operating system also has to keep track that it gave this page frame to process A page 4. Now, eventually, all of memory might get filled up. So it might have to kick something out. And when it does, it'll just go ahead and update. It'll write the data to the disk. It'll update the process table. It says, oh, process A's page 4 is now getting kicked to disk. So we'll update the information here. say it's not in memory anymore, and then I'll continue on. Now, if process A ever tries to access this memory location again, it'll see that it's not in memory and throw another page fault. And now the operating system has to read the data back off the disk, put it in some other location, and update the page table. Now, when the CPU decides to switch from running process A to process B, it will need to update this pointer so that it will point to the process B's page table. And now process B can start getting assigned memory locations or page frames to be able to do there. And now you got A and B, and there's nothing has to be continuous. We could just kind of mix up memory. Some of these page frames will be assigned to B, some will be assigned to A. And now the main job of the operating system will be to decide who gets kicked out when I get filled up and who do I put back in.